This is a screencast for Learning Target 47. We're going to be simplifying radical expressions. Just so we're all on the same page, we have a radical expression that is an expression that contains at least one radical symbol. When we're talking about terminology, the index is the number that is either written there or implied that where I just circled in red, right kind of by the tail part of the radical symbol, which you can see labeled. The number or expression under the radical symbol is called the radicand, and I just boxed that in red. The main property we're going to be working with today as we simplify radicals is this product property of radicals right here. As long as A and B are both positive or 0, and we have a positive index, we can split apart any product as multiplication of the two separate radicals. You can also do the same thing with division, though we aren't working with that particularly very much in this particular concept. So the first example we're going to work with has the square root of 54. And we're going to be thinking about the highest perfect square that goes into 54, so we can get this into what's called simplest radical form. And that perfect square is 9, because 3 times 3 is 9. 9 times 6 is 54. Technically, we can write this as the square root of 9 times 6. And then the product property that we just talked about says we can split this apart as the square root of 9 times the square root of 6. The purpose of doing that is we can do the square root of 9. The square root of 9 is 3. And then we would leave the square root of 6 there because when we take square root, we get a decimal. So we rewrite the square root of 54 as 3 square root of 6. I can do something similar with the square root of 80. Again, I'm looking for the highest perfect square that goes into 80. That happens to be 16. We can rewrite the square root of 80 as the square root of 16 times the square root of 5. Square root of 16 is 4, so we can do that and leave our square root of 5 there. Remember, too, we can read these answers as radicals, so it could be 3 radical 6, 4 radical 5, and so on. Now, when we bring in variables to it, we will actually be doing, we can bring in some absolute value symbols. For example, if I'm taking square root of x squared, we would write this as the absolute value of x. This only happens when we are taking even root of the same even power. In other words, it doesn't work for square root of x to the 4th. If I'm doing cube root of x cubed, we don't need that absolute value bar there. The reason why we put this here is we don't know whether a ends up being positive to start with, and we want to make sure we have a positive answer. Our main principle we are using here today when we're working with variables is, as you may remember, when you raise a power to a power, for example, if I take x cubed and square it, we multiply 3 times 2 and end up with x to the 6th. So if I'm doing the inverse operation, which in this case would be taking the cube root potentially, or the square root, I'm sorry, of x to the 6th, we would take that power of 6 and divide by 2, or in other words, end up with x to the 3rd. So an example of something like that might be square root of 49, x to the 4th, y to the 6th. I can take square root of 49 at 7. I can take square root of x to the 4th because it's an even power. 4 divided by 2 is 2, so we get x squared. I can take square root of y to the 6th. Again, even power. 6 divided by 2 is 3, so we have y to the 3rd. Similar idea, we have square root of 81, x squared, y to the 12th. Square root of 81 is 9. Square root of x squared is x. Even root, even power. They match. Absolute value of x. Take y to the 12th. Square root of y to the 12th is y to the 6th. Again, we're dividing our power of 12 by 2. Stepping it up a little bit, now let's get to something where I can't necessarily work through that as quickly. 36x to the 6th, y to the 9th. Now, the beginning part starts off the same. I can do square root of 36. I can do square root of x to the 6th, as we talked about earlier. But with y to the 9th, I can't do that square root because 9 divided by 2 gives me a decimal. So I need to think to myself, what is the highest power of y that is divisible by 2 without going over 9? Because I can't take more than a half, and that would be 8. So we are going to rewrite the square root of y to the 9th as the square root of y to the 8th times the square root of y. And the things I just circled in red, I can take the individual square roots. The square root of 36 is 6. The square root of x to the 6 is x to the third. The square root of y to the 8th is y to the 4th, dividing both of those powers by 2. And because I can't take square root of y and have it come out nice and evenly, we leave that there. Let's try another one. 40, x to the 8th, y to the 11th. Now here I can't take square root of 40, however, we can simplify it as the square root of 4 times the square root of 10. And we can take square root of x to the 8th because I can divide the power of 8 by 2. Square root of y to the 11th, I need the closest power without going over, which would be y to the 10th, leaving me with y. And again, what I am circling in red, I can actually take square roots of, and I am going to do that. And that gives me 2x to the 4th, y to the 5th. I cannot take square root of 10 and y. We multiply them back together and put them under the square root. Okay. Let's delete this page. Here we go. Sorry about that. Let's try another one. Square root of 20, x to the 7th, y to the 5th. Can't take square root of 20, however, I can split it apart into square root of 4 times square root of 5. Cannot take square root of x to the 7th, but I can split it apart as x to the 6th times x. Same idea with y to the 5th, it'll be y to the 4th times y. Again, all under square roots. Anything I am circling in red, I can take square root of, and I'm going to do so. 2x to the 3rd y squared. Anything I didn't circle, I cannot take square root of, they remain under the radical. Same idea works when we are talking about cube roots. I have the cube root of 27, x to the 6th, y to the 9th. Cube root of 27 is 3. I can divide the power of 6 by 3 to get x squared. Power of 9 divided by 3 gives me 3, and we get 3x squared y to the 3rd. Taking it a little bit further, cube root of 8x to the 8th, y to the 6th. I can take cube root of 8. I cannot take cube root of x to the 8th. However, my closest power of x divisible by 3 is 6. We can rewrite x to the 8th as x to the 6th times x squared. I can take cube root of y to the 6th. Again, anything in red that I am circling, I can take cube root of. That gives me 2x squared y squared. And we have the cube root of x squared that I could not do. Last example, cube root of 125, x to the 5th, y to the 12th. Again, I can do cube root of 125. Cannot do cube root of x to the 5th. However, if we make it cube root of x to the 3rd, we can do that. That leaves me with cube root of x squared. Cube root of y to the 12th I can do. Again, stuff I am circling in red, I can do cube root of. 5x, no bars because it's an odd root. And we've got y to the 4th, cube root of x to the 3rd. And as you hear, the bell is ringing, so that is the end of my screencast. Have a great day.